Okay, so let's start with a simple lemma.
So what's the expectation? Where's the randomness here?
The randomness is over the samples. The input. X is the input.
Oh, I see.
Okay, so let's start with a simple lemma. So there exists a global minimum of f such that the norm of this matrices are smaller than 1 over L. So this basically says that if you make the the number of layers more and more, you only need smaller and smaller matrices. I mean, this is kind of intuitive because you have a product of bunch of matrices. So if you have more products and more items, you can make each of them relatively smaller. Okay, so and this has some log factors, which is not important, I guess. So, and the theorem that we're going to prove is that if this configuration A1 up to AL is a critical point with vanishing gradient, and L satisfies that the max of the spectral norm of AI is less than half, then this is also a global minimum. So, in other words, in words, this residual neural network has no bad critical points. All critical points are global minimum. And just for comparison, if you don't have this identity connection, it can be shown that all local minima are global minimum, but they are bad critical points. So we have a stronger and more desirable properties by doing this reparametrization. Okay, I guess I can skip the proof sketch and just jump to the wrap up. So again, the punchline is that the parametrization with the identity connection makes optimization and representation easier. I guess the open question is, how do we analyze the optimization estimate of the nonlinear case? I think we are getting close. So kind of one hope, in some just to connect to the matrix completion thing. So recall that linear residual net is kind of like a test case for us to understand the nonlinear thing. This is kind of the same situation as we had for the matrix case, right? We started with a simple case and we want to generalize to the complicated case. So it sounds like we again need some Occam's proofs for the linear residual net, which doesn't use all of these nonlinear which doesn't use all of these linear algebraic tools. So if you have a different proof for the linear residual network, maybe it can generalize to nonlinear case. That's just a hope. Okay. So and another thing is that maybe algebraic geometry tools are possibly be useful if you're only dealing with critical points. In some sense, the problem with dealing with local minima is that you have this positive semi-definite constraint, and it sounds like it's beyond scope of algebraic geometry because you have semi-definite. This is kind of like real algebraic geometry, right? You have inequalities, and however, if you believe that we can only deal with critical points, then the algebraic geometry thing might be useful because you don't need real algebraic geometry. That's a big relief, I guess. But that's just some hope. Okay, I guess I'll stop here. Thanks.
Questions, comments? I'm actually curious about the slide you skipped. I mean, how did you go from the statement that you have like all the critical points? Can you go back to 2 slides and?
Oh, the proof sketch?
Yes. So.
It's very simple. So let's do it. So it's very simple. So we calculate the gradient. Just believe me, you can calculate gradient. Gradient is like this. The gradient is a product of a bunch of things, right? Some of them are I plus AJ transpose. And there's an E here, there's a sigma here. E is the error, basically. So how well your network fits the linear transformation. And sigma is the covariance of the data. And let's assume that sigma is well conditioned. The least singular value of sigma is strictly larger than 0. And then also note that because each of the AI has spectral norm less than half, then the minimum singular vector of AI I plus AJ transpose is larger than 0, actually larger than half, by triangle inequality. So that means that this is a bunch of things, a product of a bunch of things, except E, here all of the other things are well conditioned, like have singular least a singular value larger than 0, and if the gradient is 0, that implies that E is 0, and E is 0 means that it's global optimal. So that's also, this is strictly simpler than a case when you don't have this identity connection. Like there, it requires a more subtle analysis, like complex analysis.
So, in real problems, real deep learning problem, or this resonance or something, is there evidence for or against the statement that really something as strong as this is true, that all global minima are local minima, or something like that? Or is the suspicion that it's more complicated, but that's approximately true? Or maybe there's just no evidence anymore?
I think there's no evidence against them. So first, let's say take the weakest one. So the all local minima, global minima. I think at least there's no really evidence against it. And actually, in fact, there's evidence that supports it because
I don't believe that. It could be that that the global minima is 0, and probably you can show local minima which are above 0.
But I think but also what exactly you mean by neural network? Is it for one?
But even a few layers.
So the empirical evidence.
Empirical evidence.
So in this case, I guess in this case for the linear ResNet, the empirical case is not really local minimum even. I think people was more excited about how fast the trend. Right? That's the first order effect. And the local minimum with or without it, that is my reading.
Sorry.
So with local minimum now get different result. There's not, people say all comparable, but people are excited about how much faster training. That's the main thing. You can cover things much faster.
And there's another issue that often people are training these networks for random initialization that the networks don't converge. So clearly
don't converge?
No, convergence. At least with the very large computer vision classification tasks. I definitely know that there are cases where people have trained the networks from some starting points. It's not giving them good results.
It's not clear what happens. So first of all, for most of the successful case, of course you can design some weird case so that it's not true. But in all of those successful cases, at least for now in computer vision, the training error is always 0. So you can even have at least it converges to global minimum. 0 is the minimum that you can achieve. So this is the evidence that supports this thing. And also regarding the initialization, sometimes you don't really know what happens. So for example, if you initialize the weights to be too large, then it's possible that you just need a smaller learning rate, or it's a very weird place which you can rule out by other means. When I'm saying that all local minima, global minima, this we should take this. It's not
mathematical.
It's not a completely mathematical. For example, you can say, okay, in this region, all local minima, global minima. That's also fine, right? So, but I believe that that's at least partially the reason for why all of this can be trained. Also, for example, another example is that if you initialize all of weights with negative numbers, then you are going to have a critical point, right? The gradient will be 0 because the ReLU zero out everything. So that's another bad example. However, those things shouldn't count, right? When you talk about this kind of things.
All right, let's thank you again.
There's a